every regular language is defined by some finite state automata, but what can we actually do with regular languages? What sorts of regular languages are out there? And we've seen a few examples already, such as on 3 letters, ABC, the language of words that have an odd number of A's and no C's in them. And we've seen a language of valid addition facts. But what other languages are out there? What else is available? Well, let's start with some really basic things. For instance, we know that the empty language, the language that has no words in it, is a regular language. We'll write this as the empty set because it is the empty set, and it's very easy to create an automaton that accepts exactly the words in this collection. So this is a regular language. The next simplest thing that we could ask for languages that have only one word in them. So for instance, we might want to talk about the language that just has the simplest word, the empty word, the word that has no letters in it. Remember that we want our words to be sequences, finite sequences of letters from our finite alphabet. And in order for the structure to behave nicely, we want to include the empty word in there. Very often, if you're working with a programming language, it'll have the empty string. You can have a string with 0 characters, and that's a really important thing to be able to talk about. And similarly, in mathematics, it's really important to have a string with no characters in it, just like how it's really important to have 0 within your natural numbers to kind of make the structure complete. So we denote this empty word, this word with no characters in it. Well, I can't write it out on the board because, well, I wouldn't be writing anything. So we can, for instance, use epsilon to represent the empty word. And so the language that contains just epsilon, I'm actually also going to want to refer to this language as epsilon. It turns out that it's unambiguous to refer to languages that contain a single word by that word itself, and this is actually common practice. So I'm going to refer to this language that only has the empty word in it by epsilon as well. And of course, we'll refer to the empty set language just with the empty set. And then what's the next simplest thing that we can do? Well, let's say that we only have 2 letters. We have A and we have B. Then we can have the language that consists of just one word, and that one word is just the letter A. And again, along the lines of referring to our singleton languages by the word in that language, we'll want to refer to this language as A. And of course, we can do the same thing for B. We use B to refer to the language consisting of just one word, that word which consists of just one letter, which is B. So these are our basic languages, and what we can do is we can combine them together to build up more complicated languages. For instance, we can concatenate 2 languages together. Let's say that we have a language L1 and L2. Then their concatenation, and I'm just going to write this the same way that we write concatenating strings together, by just concatenating their symbols. Sometimes mathematically it's convenient to write concatenation of 2 words. Let's say we have a word W and a word V. We can write that with a vertical. This is actually a superscript frown symbol. This is a common way of writing concatenation in situations where just concatenating the symbols would be ambiguous. But we hopefully won't run into any sort of situation like that. So I'm just going to write, if I want to concatenate 2 languages or concatenate 2 words, I'm just going to write them next to each other. So here we have 2 languages, 2 collections of words, and if we want to concatenate them together, all we need to do is take the set of all concatenations of one word from the first language and another word from the second language. So we take every possible combination of something from the first and something from the second language, and then we concatenate them all together, and we get this new collection of words, which is our new language. So for instance, if we want to take some of our base languages, we can concatenate them together. Let's take our language A, which consists of just one word, the word A, and our language B, which contains just the one word B, and concatenate them together. And luckily for our notation, this refers to the language that just contains the concatenations of something from A and something from B, which there's only one, because there's only one thing in each of these languages. There's only one way of concatenating this. And so it's literally just going to be the language containing just one word, that word being AB. So again, this builds on this idea that we're going to, anytime we have a language that has just one word in it, we're going to refer to that language by that word. This is a perfectly fine and common thing to do. But we can also do this with other languages that we've seen before. We can take the language of the set of all words that have an odd number of A's in them, and then tack an A onto the end, and that's going to be the language of words that have an even number of A's and at least 2 A's, and that ends in A, and I guess also doesn't have any C's in it. And of course, it's important to note here that if we have two languages, and these are both regular languages, then their concatenation is also going to be a regular language. That if we have a finite state automaton that recognizes language 1 and a finite state automaton that recognizes language 2, then we can construct a finite state automaton that recognizes the concatenation of the two languages simply by taking those two automata, and we have to kind of thread them together. One way of doing this is to take all of the edges that are leaving the start state of the second automaton and have those edges also be leaving the end state of the first automaton. So kind of complicated. This proof is a little bit simpler if we allow our transition diagram to have what are called epsilon edges. These are edges from one state to another that we are allowed to traverse for free without using up any of the characters of the input. And it turns out that we can add these to our notion of what it means to be a finite state automaton without actually changing the expressive power of what it means to be a finite state automaton. And if you add that, it's as simple as adding an epsilon edge from every final state of the automaton for L1 to the start state of the automaton for L2. Another operation that we can do is we can take two languages and we can take their union. And I'm going to denote this. There's many different ways of denoting this. I'm actually going to denote this using the computer scientist's large vertical bar, L1 vertical bar L2, to indicate that a word is either part of the first language or part of the second language, right? That's what it means to be part of this language. You are either part of the first language or you're part of the second language. And it's actually really straightforward to produce a non-deterministic finite state automaton recognizing this language given a finite state automaton for L1 and a finite state automaton for L2. You just have the two state diagrams be two separate things, and then what it means for there to be an accepting run is either there's an accepting run from the start state of the first automaton to an end state, or there's an accepting run from the start state of the second automaton to an accept state. And because these two state diagrams are disjoint from each other, that means that either the input word has to be a path from the start state of the first automaton to an accept state of the first automaton, or a path from the start state of the second automaton to an accept state of the second automaton. So this recognizes exactly this language here. And we can use this construction to combine together the languages that we already have. Taking our basic pieces and combining those together with concatenation gives us any language that has just one word in it, right? We just put the pieces together using concatenation to have the language that has just that one word. And then, if we want to have a finite language that has some finite number of words, we can take the union of all of those finite words. But we're not allowed to do these operations infinitely, so we need something else to give us infinite languages. But once we have concatenation and union from these basic languages, we're able to produce all of the finite languages. Another operation that we can use to build new languages out of old languages is the Kleene star. So this operation here, if we have a particular language, L star represents the set of all concatenations of some finite number of words from that language. And this could be one word from the language, it could be 0 words from the language, so this is always going to include the empty word, and it could be 100 words concatenated together from this particular language. In fact, the Kleene star is used to denote the entire language. If we wanted to, we could take the set of letters within our language and take the Kleene star of that, and this is going to be the set of all concatenations of letters A and B of any length, including length 0 and including length 1, including length 2, and so on and so forth. So what this does is it gives us all words that consist of the letters A and B. And so if we use sigma to represent the set of letters, the alphabet, then we can use sigma star to represent the set of all words on the letters A and B. Again, including the empty word and including words of length 1, specifically A and B. And if we want to produce a finite state automaton that recognizes these sorts of words, we essentially just need to wrap around our finite state automata. We need to take the start state and we need to make it an accept state as well, and then we simply have epsilon edges from all of the accept states of our finite state automata and have them wrap back around to the start state. So you could, for free, after reading a valid word of the language, go back to the start state and get ready to read another word. So it turns out that starting from the basic languages that I showed you and applying these 3 operations, we can get to any regular language. This is a remarkable result, and it's known as Kleine's theorem. And I'll talk about kind of the proof behind it in just a moment, but I want to talk about what we've done here. We had a set that we started off with, and then we had some operations that we could apply to that elements of that set to produce new things. And then we simply took the set of all things that can be reached from this start by applying these operations. This is the process of generation, right? We have a base, and then we have some operations, and from that base we use those operations to generate a large collection of things. It's going to be closed under those operations, it's going to contain the base, and it's going to be as small as possible. And this shows up everywhere within mathematics. I can't think of an example of an area of mathematics that doesn't have this sort of construction somewhere in it. And there's several really nice things that happen whenever we do this sort of construction. The first one, and the one that's most relevant to this video, is that we wind up getting expressions for everything that can be generated in this way, right? We have some sort of formula that describes how we, starting with the basic pieces, put those basic pieces together, what order we applied operations to those pieces in order to produce the element of the collection that we wanted to talk about. In this case, some sort of regular language. And this expression that describes applying these operations in this particular order to the basic pieces is called a regular expression. And we always get those. Anytime you have some sort of generation situation where you start with a base and you apply a bunch of operations to get a wide variety of things, you're always going to be able to talk about things that you can get via that construction using formulas, using expressions. And this is a very powerful tool because we can reason about formulas in a mathematical way. So again, we have our regular expressions. These aren't quite the computer science notion of regular expressions. Regular expressions in computer science allow you a few more things. For instance, there's plus, which is a modified version of star, which lets you concatenate more than one thing together. And we don't have that here because we don't need that. Typically, regular expressions in computer science give you more tools that don't expand the expressive power of regular expressions. They're still going to define regular languages. It's just that they're more convenient tools. And in mathematics, we don't care so much about that. We want something that's mathematically very simple so that we can reason about these formulas without having to worry about having a whole bunch of different notations that could make up a single regular expression. Other examples of generation in mathematics include polynomials, right? We start off with numbers and x, and we apply addition and subtraction and multiplication and combine those things together to get new polynomials. And in fact, just generally speaking, algebraic expressions consist of starting with some basics, just basic numbers and variables and maybe some functions, and combining them together in some limited number of ways to get all sorts of things. And it's very useful, it's very powerful to be able to reason about these formulas as mathematical objects. Logical formulas are also built up in this way. We start off with some small basic set of symbols and we can combine them together in very precise ways to wind up producing this logical formula. And because these logical formulas have been put together in this well-structured way, we can reason about them. If you take a look at the axioms of set theory, there are two axioms that specify the existence of an empty set and the existence of a particular type of infinite set. And then from those, the rest of the axioms say that you're closed under certain operations, certain set theoretic operations like pairing or union or power set. And then from those basic sets, you can construct other sets using these operations. And it's also common to construct the natural numbers by saying start with 0 as a base, and then we can apply the +1 operation as many times as we like. So having access to these regular expressions, once you get used to working with them, really can help you develop a strong intuition for what sorts of things we can and cannot do with regular languages. For instance, one of the questions we might ask is, what can we do with just one letter? Well, we could have, for instance, the language of words that have a number of a's that is congruent to 2 mod 3, or we could have the language of words whose number of a's is congruent to 2 mod 3, but is at least 8, right? So we could have this segment of a's, and then this star piece could represent 0 copies of 3a's in a row, or it could represent 1 copy of 3a's in a row, or it could represent 2 copies of 3a's in a row, or so on and so forth. And this will produce the set of all words that are 8 plus 3 times k for some number k. And it turns out we can union this sort of language together with other languages of this sort and other finite languages to produce this wide collection of possible regular languages on just one letter. We can also talk about, if we have 2 letters, we can talk about those words which have something followed by ABBA followed by something. And what this language refers to is it refers to the set of all languages that have the sequence of letters ABBA somewhere in them. ABBA with some word, possibly empty, concatenated onto the front, and some word, possibly empty, concatenated onto the end. We can also refer to the regular language that consists of words on the letters A, B, and C that contain an odd number of A's and any number of B's and no C's. These words consist of some number of B's, followed by an A, followed by some number of B's, followed by a word that consists of any number of B's located anywhere throughout it, but it has to have an even number of A's. And in order to do that, we need to have words that have two A's in them. So this here is a word that has two A's in it with possibly some B's interspersed throughout. And then if we take those words that have two A's in them and we Kleene star them, we get words that have an even number of A's, right? Some number of concatenations of words that have two A's in them. And if we concatenate that with a word that has exactly one A in it, then we get words that have exactly an odd number of A's in them. So sometimes it's really easy to see that something's possible by looking at a regular expression, and other times maybe it's easier to use our intuition about state diagrams. Having a wide variety of perspectives on regular languages gives us lots of different ways of building up regular languages. But is this everything? We've seen how we can use the way that a regular expression has been built up to build up a finite state automaton that recognizes that particular regular language. But what about the reverse? If I have some sort of finite state automaton, can I turn it into an equivalent regular language? And the proof of this is absolutely ingenious. We can construct a regular expression recursively given the graph of a particular finite state automaton. In order to make sure that this recursive process doesn't get stuck in any infinite loops, we will be calculating the regular expression for a particular transition graph in terms of the regular expressions for transition graphs with fewer edges. And so all we need to do is make sure that we work out what the regular expressions are that correspond to graphs, finite state automata whose graphs have no edges in them. Well, I'll let you work out what the regular expressions are. So suppose that we have some sort of transition graph and we want to convert it into a regular expression. It will look something like this. We'll have, let's say we only have one start state. The argument is the same if we have multiple start states. And we'll have an edge picked out randomly going from a state S1 to a state S2. And let's say that this edge is labeled A. If we have a word that's accepted by this particular finite state automaton, it's going to correspond to the labels when we read a path from the start state to the final state. Now, it may be the case that this path doesn't actually pass through this edge. It may be the case that if we deleted this edge, that the path that we take, the word that we enter, is still a path from the start state to the end state. In which case, it's going to satisfy the regular expression for this reduced graph, where we remove this particular edge. Remember that we're going to work out what the regular expression is for this graph that has this edge in terms of the regular expressions for graphs that have this edge removed. And so we're going to refer to that regular expression of paths from the start state to final states that don't pass through this edge at all by R0. This will be some regular expression that we get. We remove this edge, we calculate the corresponding regular expression. Again, this is recursive, so we're going to do this calculation by removing an edge and calculating those regular expressions and so on and so forth until we've removed all of the edges. And I'm going to remind us that this is a path from S0 to final states of the original automaton. And I'm going to label the fact that this does not contain this edge here. So this handles the case where the path corresponding to our word from the start state of the original automaton to a final state of the original automaton did not pass through this particular edge. But what about the case where it passes through this edge exactly once? Well, in that case, we're going to want a path from S0 to S1, and then we're going to take this edge by reading an A from S1 to S2, and then we're going to want a path from S2 to a final state that doesn't pass through this edge. And so what that's going to look like, well, a path from S0 to S1 is simply a word that is accepted by the automaton with exactly the same graph. It's going to have this edge removed, and it's going to have this as a start state and this as our final state. We're going to take the final states of our original graph and forget about them, and instead have this as a final state. It's going to be the same graph. We're just going to change up the labelings of which states are final so that we're calculating the paths from here to here as opposed to from here to some final state. Because this graph is also missing this edge, right? Remember, we want paths from S0 to S1 that don't pass through this edge. Because this graph doesn't have this edge in it, it's also going to be a graph with one fewer edge, and therefore it's something that's safe to recursively calculate the regular expression for. So let's call this R1. And I'm going to remind us that this is going to correspond to paths from S0 to S1, again, which do not contain this particular edge. And then we're going to want to be able to talk about the paths that take us from S2 to some final state of the original automaton. Again, same transition graph, except instead of changing up the end states, we're actually going to change up the start state. We're going to have S2 be the start state. And again, because this graph has one fewer edges, it's safe to recursively call our constructor function to construct a regular expression from this graph. And so I'm going to call the regular expression that corresponds to paths from S2 to a final state of the original automaton, I'll call this RF. So we have two possibilities that we've handled here so far. We have the case where we have a word that corresponds to a path that goes from S0 to a final state of the original automaton, not passing through this edge at all, and that will correspond to this regular expression here. It could also be the case, so we want to kind of union these languages together, we want to consider this as another possibility. It could also be the case that we pass through this edge exactly once, going from S0 to S1, and then along the edge, and then from S2 to a final state. This is going to correspond to a word which satisfies the regular expression R1 A RF. Right? Some path from S0 to S1, it's going to take A from S1 to S2, and then it's going to take RF from S2 to a final state. It could also be the case that this path takes this edge twice. In that case, we're going to go from S0 to S1 without passing through this edge. Then we're going to go from S1 to S2, passing through this edge, reading an A. Then we're going to go from S2 back to S1 without passing through this edge. And again, we can recursively find a regular expression corresponding to the various words that will take us along that path. I'll call this RL because it's the loop. So we can go from S0 to S1 along the path for A, from S2 back to S1 along the path for A, and then from S2 to a final state. And that corresponds to all of the words that will take us along a path that passes through this edge exactly twice. What about 3 times? Well, it's going to look something like this. We're going to go from S0 to S1 along this path A, back from S2 to S1 along this path A, back from S2 to S1 along this path A, and then from S2 to a final state. And so on and so forth. Now, a path of the original automaton that takes us from a start state through this particular edge any number of times, and then leaves us at a final state, is going to be the union of this infinite collection of regular expressions. Well, that's no good. We can't construct an infinitely long regular expression, but luckily, this union happens to be something that we can write in terms of the Kleene star. In particular, it's going to be R0 or R1A followed by some number of RLAs, possibly 0, but possibly many more, some finite number, followed by an RF. And then, of course, there's still this possibility R0, where we go from S0 to the end state without passing through A even once. So we need to include that as a separate part of our regular expression. And so, once we've recursively worked out all of these regular expressions, we can combine them together in this template to produce a regular expression for the graph where we had this edge, for our original graph. And this recursive construction only depends on the regular expressions for graphs that have one fewer edge, so we don't have to worry about this recursive construction going into any loops or taking forever. One final thing I'd like to note is that here we have a translation process where we can translate back and forth between finite state automata and regular expressions. And whenever you have this sort of back and forth translation process, it's always worth asking, what happens if I translate and then translate back? If we take a regular expression and translate it into a finite state automaton recursively, and then translate it back using this particular procedure, it's probably just going to be a much grosser regular expression. But if we take a finite state automaton and translate it recursively into a regular expression, and then translate that regular expression back into a finite state automaton, what this actually does is it untangles our transition diagram. Our transition diagram can consist of a web of connections where nodes are connected however they want. However, if we look back at the sorts of transition diagrams that we got when we were constructing regular expressions, there's essentially only three things that you can do. You can chain together the automata for smaller regular expressions, you can have branches where you choose one of several possibilities, and you have loops that correspond to the Kleene star. And so what you wind up getting is a finite state automaton that consists pretty much just of loops and branches. You've taken a potentially tangled mess and kind of untangled it. And I'm sure there's a really interesting theorem in there somewhere, but I haven't been able to work out what it is. So if you know, let me know. And this process of translating and then translating back will wind up being helpful in future videos in this series. So thanks for watching, and I hope to see you in a future video.